Like many of the excellent theoretical talks of this conference, this talk will concentrate on the data from my own laboratory. And I want to say that that's not because I think it's the greatest data. It's because it's the only data that I know and feel comfortable talking about. And in fact, I mean, there's even aspects of my own data that I don't understand, and so it would be doubly irresponsible of me to try to speculate about the interpretations of other people's data. So you'll tend to find experimentalists talking about their own work maybe a little more than is appropriate. However, it's simply because it's the data that we know. It's the data that I know. And another aspect of this being an experimental talk is I think that particularly for those of you who are theoretically inclined physicists or aiming for a career in theoretical physicists or are theoretical physicists, this is a great opportunity to ask questions because there's no base level of stupid question, because it's outside your domain of expertise. So you can really ask anything, really anything. How does a lock-in amplifier work? You know, just whatever you want to know, you should feel free to ask. There is no bottom limit of you know, IQ measurement that's going to be implied by how people about how your question is interpreted. So that's a license to do it, and I hope that you do it. And then maybe one last thing, which is I don't think you should take notes. I think that there's a lot of visual stuff that I prefer that you're actually kind of looking at the data and thinking about the data. And there's not much to write down. I think that these talks are all going to be online or something. And if you want my slides, I can send them to you. So I don't think taking notes is a good idea. I think you should just watch the data as it appears. Okay. I have 2 talks to give, and I have 5 topics. So I don't know exactly how those are going to get divided. Let's see how the time goes. Topic number 2, I will try to address something cultural or sociological going on in the field of Majoranas and zero-mode physics, which is a lot of the argumentation that you hear going on online, on the archive, on Twitter, if you happen to listen to that. So, you know, and again, nothing's off limits for asking me questions, so you should feel comfortable asking whatever you want to ask. Then a couple of maybe like special-ish topics, that is particularly cool, I think, experimental approaches to zero modes that go beyond just hunting for zero bias peaks in nanowires, which, you know, is fun and important, but it gets boring after a few years. And so it's a temptation to try to do other things that are other kinds of systems. And in fact, you can even discover some things that give you abilities that you don't have under the normal circumstances. So the last 3 topics about a pseudo-Zeeman route to topological superconductivity, vortex route, and planar Josephson junctions will be 3 kind of special topics. The last topic is designed to dovetail into Addy Stern's presentations. He and I talked about what he's going to cover and what I'm going to cover. And so that's the plan, that when topic 5 ends, or gets as far as it goes, Addy will kind of do some things that picks it up from there. Oh, okay, well. That would be a shame if I had to come all the way over here every time I needed to click. Well, this you've seen many times, and Jason kind of derived versions. Yeah, I have it here. I did it. I know it worked eventually. If I came over here, it worked. Okay. I just wanted to point out that in this paper in 2000 that Alexei Kitaev couldn't have done a better job of making the results obscure, not only publishing it in this journal, I don't even know how to pronounce it, but not even in the journal. In fact, he published it in the supplement to that journal, and then put maybe what was the most important, from an experimental point of view, key observation in the supplement of that journal in a footnote. Now I know that that the history of quantum mechanics is that the interpretation of the wave function entered into quantum mechanics through a footnote. So there's a great tradition in our field of putting key pieces of information in footnotes, which you can even do in your own work as a humorously going forward. But in this particular case, the point that I want to make is Kataev already recognized that this separation, as Jason emphasized in his talk, in fact, I'm taking pictures from Jason. He's a great artist, and I don't know what software you use, but you're going to see peppered throughout my talk, and I try to give credit if I forgot every once in a while. They're mostly from Jason. That the system not only makes this very interesting physical system, but already recognizing as early as 2001 that they would form qubits that would be immune to decoherence was already part of the thinking at that point. Now, what happened when people started thinking about putting a one-dimensional conductor on top of a P-wave superconductor is the first thing that experimentalists thought was, where do I get a one-dimensional conductor? And then the second thing that they thought was, and then where do I get a P-wave superconductor? But the nice thing about that footnote underneath is it says it appears that only a triplet or P-wave superconductor in the three-dimensional substrate, this substrate with a theta on it, can effectively induce the desired pairing between electrons. It wanted to proximatize to a P-wave superconductor. And if this thing, so you should start with a P-wave superconductor. And then he puts, as an afterthought of the footnote, at least this is true in the absence of spin-orbit coupling. Now, it's going to turn out that this is going to be annoying, I think. Let's see if I can just do it this way. Some decade later, the papers that motivated experimentalists recognized that by combining the key ingredients, and I think almost everyone in the room knows this, so I'm not going at, in case it's not obvious, I'm not going at education speed. I'm going at getting us on the same page speed. So, if I should be educating you because you don't know this, then you should raise your hand and say, you're going too fast. I'm looking around. No, okay. Good. So, the addition of spin-orbit coupling into these one-dimensional wires, and I'll show you what these wires are because we live in a three-dimensional world, so somebody has to construct something that's effectively one-dimensional, has, in the presence of sufficient spin-orbit coupling, a topological phase that occurs at large Zeeman energy. And in that topological phase, the Majorana zero modes appear at the ends of the wires, and that was the key piece of, I would say, a contribution of these two nearly back-to-back, I mean, a couple months apart, excuse me, papers. But what these papers really did that was particularly useful from, let's say, my point of view, or from the point of view of the experimental community, is they plugged in the numbers. They said, you can't go to 1 microdegree, and you can't have spin-orbit coupling arbitrarily large, and you can't have a 100 Tesla magnet. So the fact that there's a Zeeman term and a spin-orbit term and a temperature and all this stuff doesn't matter unless you put in how cold does a real dilution refrigerator get? How much spin-orbit coupling is there in indium arsenide? How big of a magnetic field can you apply before the parent superconductor shuts off? And by putting in those numbers and seeing that there was a pretty comfortable zone in which this would work with realistic materials and realistic equipment, that was the key advance to my eye, to my read, of these important papers, was that it became something that was pretty easy to make happen. Now, these one-dimensional wires, what I mean, and what most people mean by one dimension in the physical world, is that 2 of the 3 dimensions are in their lowest quantum state, or near their lowest quantum state. Actually, the question of what those transverse directions are, whether they are smaller than the Fermi wavelength, whether they're smaller than the phase coherence length, whether they're smaller than some spin-orbit length, depends on the physical system. What might get called one-dimensional or pseudo-one-dimensional or quasi-one-dimensional depends a little bit on what the physics problem is. In this particular case, it meant getting toward the lowest mode, or the smallest few modes, meaning that the length scale had to be comparable to the Fermi wavelength in these materials, which, by the way, doesn't happen very easily in metals, as an example, where the wavelength is like an angstrom. But in the semiconductor, because the effective mass is so light, the wavelength can be long. It can be long enough that technologically you could make the transverse directions of the wires be comparable to a half wavelength so that you can get to the lowest quantized mode in these wires. So it's like a free motion in one direction and quantized out in the other two motions. And this is the way that these nanowires were grown. It's a remarkable process. If you don't know about this way of growing nanowires, you can see at the end of the wire, there's a little gold ball. And what happens is the gold ball is evaporated onto the surface inside of a molecular beam epitaxy machine. In this particular case, it's different kinds of growth techniques. This is called a VLS growth method for vapor, liquid, solid. And the solid in this case is the gold ball the liquid is the gold ball that when you put this in the environment catalyzes the growth of the crystal, and the crystal just rises up underneath. You can even see in this electron micrograph. This is a remarkable micrograph. This is the indium arsenide crystal rising up from this growing gold ball that just then gets pushed up into the air as the crystal grows underneath it, growing the nanowire, leaving behind this atomically precise, more or less, with some defects that are important, one-dimensional wire that grows underneath the gold ball catalyst. So that would give a wire. And then you can do the rest of the ingredients that those two papers from Oreg and co-workers and Luchin and co-workers told us to put together. Now, as an experimentalist, the next thing you want to know is, okay, let's say I do all of those things. What do I look for? What's the signature that there's, they're not going to be red balls at the end of a blue wire. You've got to measure something. And so a whole series of papers that came out in the years following the Luchin, Oreg, and other related papers said, if you tunnel normal electrons into a superconductor below the gap, you'll find that they won't go in. There isn't states for single electrons. But if you inject electrons into the ends of the wire, there will be a density of states for normal electrons just at the ends. So that if you can tunnel into the ends of the wires, you'll see that electrons will go in. If there are Majoranas at the ends. If there aren't, it's difficult to tunnel in. You get high resistance when you try to tunnel into the end of a wire. Of course, you can tunnel in above the superconducting gap. But if you try to tunnel in at low energy, below the gap, nothing will go in and you'll get high resistance, unless there's something living at zero energy that lets you tunnel in. So there was all kinds of theoretical work that said, as you turn up the magnetic field to cross yourself, as you remember from that phase diagram, from the trivial into the topological region and the appearance of a zero energy state, that the states that live up in the gap will move down and reach zero, and then rather than crossing each other, will persist at zero energy, and you'll measure in conductance something which is a proxy for the density of states. If you tunnel with weak tunneling into a superconductor, the tunneling conductance, the current that you inject at a certain voltage, will reflect the density of states, like Fermi's golden rule, it's proportional to the density of states. If the conductance is not weak, if the tunneling is not weak, then there's all kinds of other more complicated things. In fact, there's an enhanced conductance in it. But at weak tunneling, you measure the density of states. So if you weakly tunnel in, this is now, the previous graph was a density of states calculation. This is an advance because this is a conductance calculation. Now we're getting pretty close to what somebody in the lab could actually think about with a voltmeter trying to measure. And it didn't take that long between when the ideas and the numbers were plugged in and here's what you ought to measure and here's what it ought to look like before the Delft group published this paper, in which the remarkable observation being that at zero external magnetic field, indeed at low energy, lower than the gap, it was very hard to tunnel in to a nanowire that was coupled to a superconductor injected via a tunnel barrier into the end of a wire. But if you turned up a magnetic field that was approximately the magnetic field that brought you into that regime of the topological region, namely when the Zeeman energy was comparable to the superconducting gap, E Zeeman was comparable to the superconducting gap, then something happened. Something showed up. A peak appeared. Whoa. Why was there a peak in the density of states or a peak in the conductance at suddenly appearing? Now let's go, okay, it's split and it did some other things and then there's some big red blob over there. But roughly speaking, this was very hard to tunnel into until you got to a magnetic field when for this material, the Zeeman splitting matched the gap and all of a sudden there was a zero energy state. So the title is completely appropriate. This was the signature of Majorana mode. And when I get to this second part of the talk about like what's going on and why we're being cautious, it's important to keep your mind open to the direction of the logical arrow between here's what the data looks like and here's what's going on inside of the material. We use all kinds of expressions like signatures, smoking gun, we heard in the previous talk. And each of them means something, and they mean different things to different people. But what they mean is usually that the arrow goes from the phenomenon to an interpretation. So this is a perfectly appropriate designation, that there was a signature that doesn't say, I looked inside of the wire and saw red balls. It says, if there were red balls at the ends of the wires, this is what you would see, and indeed we see it. Which, I'm sorry to tell those of you who don't know this already, but that's all we can do. We don't have any other magic red ballometers. We just measure and interpret. And there it is. There's this magnificent peak. And the other thing that I want to point out about this paper was that when you read in the press things like, oh, the 80-year search for Majoranas is over. That's not really the correct telling of the story. It's not the correct telling of the story because the timeline is much more impressive than that. The timeline was 2010, we get some papers that say, here's what you should go hunt for, and it looks like they'll be there. 2011, the papers come out that say, here's what you'll see if you do the experiment. In 2012, the paper appears. So that implies, it certainly doesn't imply that it was an easy experiment. What it implies is that it kind of worked. Like you didn't have to kill yourself for 80 years to get this phenomenon to appear. Now, what was interesting about this phenomenon was, contrary to what sometimes happens in an experiment in which somebody does an experiment and nobody can repeat it, in this case, it got repeated repeatedly. It was, within the next, I don't know what year this was, 2012, same year. Within that year, all sorts of papers came out saying, yeah, we see it too. In fact, there's even one from my lab at Harvard at the time. We see it too, we see it too. There's, you turn up the magnetic field and there's a giant bump appears, even in systems in which you might not even expect it to appear. In a way, you kind of couldn't get away from it. And you say, well, why hadn't anybody seen it before then? Well, it's an odd combination of things that probably hadn't been put together before. You need a one-dimensional wire, you need a superconductor on top of it, you need to put a magnetic field just along the wire, and maybe nobody had ever done that before. But if you did, under all sorts of broad conditions, you'd go to a magnetic field that was about the comparable magnetic field, and a zero bias peak would appear. So now people start to think a little bit. Well, that's interesting. I wonder whether there's something more going on than that. Now, a lot of that there were important papers, this being one of them from Silvano Di Franceschi, Eduardo Lee was the first author, in which they manifestly said, we're making a system which is for sure not a Majorana system. It's too short, it is made out of the same ingredients. It's a semiconductor nanowire with a superconductor at one end, and a normal injector at the other end, but it's just more or less a quantum dot. And they pointed out that when the dot has an odd occupancy, you can get Andreev states that have this kind of crossing phenomenon. And as you turn up the magnetic field, it's a little hard to see in this picture, but as you turn up the magnetic field, those Andreev bound states that live inside of this quantum dot can move towards zero under the influence of Zeeman. In fact, they split. You can see one going down and one going up. They just split because they're spinful. And the ones that go toward each other kind of meet in the middle and they get kind of blurry. And this paper made a point of, okay, the important point in the contribution of the paper was to recognize that there was this important singlet to doublet transition in the odd occupied state, but they didn't fail to mention that, by the way, this looks an awful lot like the emergence of a zero bias peak in a system in which we don't expect Majoranas to exist. So now it becomes a richer problem. And it's a problem in which there requires the participation of theorists to understand how do you differentiate between all of the various phenomena that could be interpreted in terms of Majoranas or Andreev bound states, and really what's the difference between a Majorana and an Andreev bound state when they're in a small confinement. Anyway, but I think that it's kind of fun because it's like for those of you who didn't live through this period, it's kind of a detective story. It's really unraveling year by year and even month by month when all kinds of data was flooding the literature and all kinds of theory was coming in saying, well, if we analyze it this way, we get that. If we analyze it that way, we get this. And that was what was going on at the time. So there's a lot of thinking and a lot of measuring and a lot of discussion. One thing that happened that I think helped turn the corner a little bit in the field, it wasn't a revolution, but it was a sort of a next advance, came from material science. And what happened was a researcher in Copenhagen who had just graduated, working with a young professor there named Thomas Jespersen and Jesper Nygaard, and then subsequently was working as my postdoc at the time, developed a technique for growing the semiconductor and superconductor in a kind of crystalline registry so that you didn't need to deposit the superconductor onto the 1D wire, you could just grow it. So you could grow the wire with the superconductor already integrated into it. And that helped a lot because a lot of the problem with depositing superconductor onto a semiconductor, well, I wish I could tell you exactly what the problem was. I have some guesses about what the problem was. I can tell you that I spent years myself, and I know friends who did it, who was, they would just say, run the other direction. It just doesn't work. It doesn't work probably because of oxide, probably because of disorder, probably because there's junk on the surface. But really, we didn't know why it didn't work, but it just simply didn't work. And so cleaning the surface, and it's not interesting, especially if you're a theoretical physicist, for us to have a whole lecture about cleaning the surface. But what I can tell you is, no, but it's important because it didn't work. I mean, there were people for decades trying to make superconductor semiconductor systems that just didn't work. So when the Delft experiment came, or the Weizmann experiment came, or our experiment came at Harvard, we were spending lots of time thinking about how to get the little tiny atomically thin layer of oxide off of these one-dimensional wires so that when you slap the superconductor down quickly, it made a good electrical contact between the superconductor and the semiconductor. And then there were other tricks, like why indium arsenide. Indium arsenide was very good for a really detailed reason that's as, if you're a theorist, maybe as boring as cleaning the surface, but that the bands bend in that particular semiconductor that lets electrons flood the surface. So there were some details about just trying to get electrons across that interface between the superconductor and the semiconductor that this alleviated because they were grown in the same growth chamber and they were just in crystal registry. You just literally went from atoms of indium arsenide to atoms of aluminum in a single crystal. And so that made a big difference. And when we started making devices, it wasn't like the sun suddenly came out. It was still hard to do. But when the superconducting proximity part was made out of a wire that had this epitaxial aluminum, in this case on two faces of the nanowire, then you started getting data that looked more, and and needless to say, this is among the best data that we took. There was also plenty of data that didn't look this nice. Of the Zeeman level comes down, it meets in the middle, and it goes straight. And the theory says it goes down in the middle and it goes straight. Okay, now yes. Yeah, isn't it? It sounds crazy because it's not lattice matched. The trick was the following. You have to make the substrate cold, nearly liquid nitrogen temperature, which is not something that usually lives inside of molecular beam epitaxy growth chambers, is that you can cool the stage to liquid nitrogen temperatures. And it had to be just the right temperatures because if it was too cold, then the atoms would go down and they would stick wherever they landed and they wouldn't have a time to crystallize. But if it was too hot, they would make droplets. So it had to be a temperature in which they could still kind of anneal themselves into some registry, but not so warm that they would do what they really want to do, which is ball up. And so it was a delicate balance, but temperature and growth rate proved to be the key. And it was just a matter of playing around. You could say it was lucky, fine, but it's all, now it's an art, and you'll see that there was other two-dimensional versions of this, et cetera. But once the cooling of the substrate in MBE was recognized to be of high value, lots of people started doing it. Okay, anyway, so we're now up to 2016, and we're starting to get data that, and again, if anybody says, well, this is just unarguable, this is unambiguous, well, then you haven't been listening to what I'm saying. Nothing's unarguable, nothing's unambiguous. That's just not the way experimental physics works. If you get nothing else out of this talk except that fact, that you might see this and say, oh, okay, now it's game over. It's not game over, and it will never be game over. So papers started appearing that analyzed the problem more carefully, and they said, there's all kinds of things that could be going on. Like you remember from the Differentieschi, they had a quantum dot. Well, if there was a potential modified at the end of the wire so that it made a quantum dot, you could get different kinds of zero energy states that could mean different things. Here's an example from the numerics of this paper from Moore, Stănescu, and Tawari, in which here's two examples of zero energy states. One of them of the sort that Silvano Differentieschi was looking at, and then some other stuff goes on, and then a different kind. And what's interesting is that if you plot the wave functions, this one out here is a Majorana zero mode, and the wave functions are delocalized at the ends of the wires. This is the simple numerical model of the wire. Whereas this zero crossing, they're all stacked up at one end. They're in fact living inside of this lounge chair that exists at the end of the wire. So different zero crossings could mean different things. And experimentally, we would sometimes see these same kinds of things. Here's experimental data. It's unpublished. Here's an Andreev bound state that crosses and splits again, and then recrosses and goes to zero again. So you can kind of begin to tell the story, but the real issue here is that one has to be very careful. Just to say, oh, I've brought Andreev states down to zero. Yeah, well, maybe you did something interesting, or maybe you didn't. Or maybe you didn't and then later you did. So a lot could be going on. At this point, numerics started really trying to understand what can happen in these experiments and what kind of data will you tend to get. Now, the numerics themselves became sufficiently complicated that they were almost like experimental systems. They had knobs. You turn the knobs and you see what the data looks like. And so it became also not clear from the numerics the degree to which they were looking at generic versus non-generic features. But here's an example. This is a paper from Shankar Dasarma's group, Henning Pan. And he compares a variety, and you see this generic platform re-arising, injecting from a normal metal lead into a semiconductor superconductor heterostructure under various conditions. One condition is everything's perfect. There's no disorder, the gap is constant as a function of position, the potential is constant as a function of position. That's what he called the good situation. Then there was one of these kinds of lounge chairs where there was a thing at the end and a smooth lounge chair at one end. Then let's say that there was a potential that had some roughness in it. And let's say, or maybe the G factor had some roughness in it, or maybe the gap had some roughness in it. And you start adding these things, which are kind of experimentally realizable situations, and you start to find that if you get data that looks like this and you see that something goes out and looks like a zero bias peak, sort of like the data that you were seeing, well, it could mean different things. It could mean, depending on where you cut here, 0.6 is like right here before they meet, and it looks like the wave functions are all over the place. And by the time you get up to 1.2 out here, then great, one is at one end, one is at the other end. This is the good situation. And that's a situation in which there are bona fide Majoranas to be identified from the numerics. However, there are other situations in which you get data that looks an awful lot like what you think you might want to get. And yet, if you look at what the wave functions look like in that regime, or 0.9, maybe right at the edge of where they are, they're all over the place. And these were in situations which got the name from the movie Good, Bad, and the Ugly of the ugly. Okay, so the numerics shined a light on which kinds of disorder could give you data that mimicked the experimental data. But very much like the experimentalists, these parameters were also being tuned. And you didn't get a sense of whether this was a generic or a non-generic feature. It was also a tuning knob. So if something was going to cross and then something was going to not cross, it's pretty easy to find a regime in which it just barely doesn't cross at all. And we don't know whether that's what was going on here or not. But what happened with this literature was that, again, from this same paper, you could take experimental data from the literature. This one happened to be from my lab, but that doesn't matter. This one from the Delft lab. And then kind of construct numerical models by having enough knobs that you can turn, that you could make things that, yeah, well, yeah, it looks an awful lot like that. I mean, especially this one, it's almost the same colors. And you could say, well, it's pretty hard to say. And I think what all of this gets back to is this is a very sophisticated way of showing the thing that I claimed and said at the beginning, which is we in the experimental world, sad but true, we only have a one-directional arrow. We can go from, if this were what's going on, it would look like this. We don't have the arrow going the other way that says, if you see this, that's what's going on. We've never had it, we don't have it now, and we never will. So then we start using words like smoking gun and signature and suggestive and consistent with and not inconsistent with, and this whole hierarchy of certainties. And I have to say that this is a vocabulary that experimentalists have to think about a lot, because every time we sit down to write up and describe what we've seen, math, you say it's a result. We put an equal sign. Occasionally you have to put a wiggly equal sign. Okay, but every single time we write a sentence, we have to say, this shows that, this is consistent with that, this is suggestive of that. I mean, this is all language that we spend a lot of time thinking about because we only get that one-way arrow. And these kinds of numerics are sort of bringing to the popular eye this reality of what it means to measure. So the way the game goes now is the next thing that experimentalists do given this situation is we don't argue stridently for the correctness of our results. That would be a temptation, to just have a louder voice and to say, we're right. What we do instead is we do other experiments that are hopefully require harder and harder evidence to construct models that don't, that would fake it. Okay, so we have to think of the next thing. What do we do now? We did the zero bias peak, what do we do now? So here's an example of something that we did next in Copenhagen. And this brings us all the way back to the 1990s. This is a really interesting and beautiful series of experiments led by various groups. This is a theoretical paper from Averin and Nazarov, and it's about the following system, which I'll denote NISIN. I is insulator. So that thing is a quantum dot, if you want to call it that. It's a superconducting quantum dot with normal metal leads. It's different geometrically than the system that we had before. It's like an inside-out kind of version of what we had before. And you say, well, I wonder what would happen in this case if there were zero bias peaks, blah, blah, blah. Well, it's interesting. You'll see what happens. What happened in the 1990s, and this was people working just with metals, that was just an oxide, for instance, if this was aluminum and you put aluminum oxide barriers between them and maybe gold or copper or something on the ends. As Jason was saying in his presentation, if the whole system has to have an odd number of electrons, then that odd electron will have to go up above the gap somewhere as a quasi-particle and will cost extra energy relative to an even number of electrons. Now, who knows whether or not if you have a finite piece of metal with billions and billions of electrons, whether or not there's any hope that this thing will keep track of whether or not that billions and billions number is an even number or an odd number. It seems kind of unlikely, but it turns out, and that's what this line of inquiry was about in the 1990s, it turns out that superconductors, and this is maybe the underlying miracle of topological quantum information processing. Everybody talks about, oh, the Majoranas are separated, they're exponentially separated. But because the whole Majorana quantum computing business is about parity, the real miracle that allows the real miracle of materials that allows topological quantum information processing to proceed is that you can have a macroscopic piece of superconductor and know exactly whether or not the number of electrons in it is even or odd. That's a shocker. You should not believe it until you see the data. I think your intuition would say that sounds wrong to me, that I should know if I have billions of electrons whether it's an even number or an odd number. And yet, it does it. So if I show you the data from the 1990s, the theory looked like this. Here was what the experimental device looked like. Again, don't write it down. You can find this later, 1993. If the superconducting gap was so big that in order to add the odd electron, it cost more than the Coulomb energy to add that electron, the charging energy, then that odd electron would just never go in. And you'd have a Coulomb blockaded object that only counted in units of 2. And you would have 0, 2, 4, 6. So you see the vertical axis, the average occupancy would have this staircase function. As soon as the number dipped down below this, the crossing point was where the charging energy was. When the gap got smaller, then you'd have a little step and a big step and a little step and a big step in this Coulomb blockade staircase as you added electrons. And then finally, when that got all the way down to 0, let's say you killed superconductivity, there was no superconductivity at all, then of course you have 1, 2, 3, 4, 5, and the electrons go in because there's no penalty for an odd electron if there's no superconductivity, if the gap goes to 0. So this was done, and it was validated extensively. And we tried to bring that idea, which of course meant the first thing that we needed to do was find out whether or not these nanowires were good parity objects. Turns out they were. So here is what Coulomb blockade looks like. Now the vertical axis of this graph is the source-drain bias. I hadn't talked about that variable yet, but let's just say it's 0 for a moment. If the source-drain bias is around 0, then you get Coulomb blockade peaks. And what you can see here is Coulomb blockade peaks that are, you have to trust me that they're evenly spaced in 2e, but I'll bring the magnetic field, I'll turn up the magnetic field, and that lowers the gap. And what happens is then you have little step, big step, little step, big step. And then finally, when the magnetic field gets around 220 millitesla, you have evenly spaced Coulomb blockade. Now, for the careful observer, especially the observer who's not taking notes, but just looking at the data, you'll see something interesting, which is that there is structure inside of those Coulomb blockade peaks. Those are not metallic-looking Coulomb blockade peaks. Those are states in which there's subgap structure. 220 millitesla does not drive the system normal. These are evenly spaced not because it's normal, but because a level has moved down to 0. And now even and odd occupancies are equal energy. If it's an Andreev state and it's away from 0, you get little step, big step. And if the Andreev state is all the way up at the gap, you get 2e. So here's this level moving down from bigger than the charging energy to smaller to all the way down to 0. And yet you can see the structure that shows that it's not, that there's a subgap discrete spectrum. I'm going a little fast because this is a rather old experiment and I want to get to the modern versions of things. As I turn up the magnetic field, a very interesting thing happens, which is you see these 2e Coulomb blockade peaks. It goes dark, and then it comes back with half the spacing. I can keep very careful track of the spacing of those Coulomb blockade peaks, and I notice something remarkable. What I notice is that when they're 2e spacing, and I measure the spacing between Coulomb blockade peaks, I've only got even peaks, so there's only a red curve, there's no blue curve. And then suddenly this drops by a factor of half, and it becomes 1e spaced. Almost 1e spaced. Not quite. Because the wire's not long. So the states really aren't at 0. they're near zero. And the Coulomb blockade reflects the fact that this oscillating structure is keeping some kind of track of where those levels are as the magnetic field is turned up. And the oscillation amplitude, well, what does theory predict? Theory predicts that some measure of this oscillation amplitude should tell us how long the wire is. Because as the wire got farther and farther away, they should really become at zero energy. So then we have a harder job, which is to do the experiment a whole bunch of times with all different length wires and see whether the amplitude of that oscillation here, what I called A, actually falls off exponentially. And in this experiment, wouldn't have published it unless it did it, but here's the amplitude A for a short wire, just under a micron. Here we go up to 1.5 microns, and this thing falls off. It's not a huge amount, and it was okay. It was the best we could do at the time. But it was a next thing. That's what I think the important point is. And again, don't think, oh, well, that locks it in. Now we're done. Now we've definitely shown their Majorana is okay. Let's move on to the next thing. It's not like that. Now, of course, the next thing that happens is the theory papers start to come out saying, well, we thought about this experiment and we made the quantum dot and we put this thing in and we see how the levels go down and we see how the Coulomb blockade peaks go. And when the Majoranas, when it's less than delta, you get this kind of a peak, and when it's greater, and then when it's a Majorana, you get that kind of a peak, and it should go up, then down, then up, and the brightness should go down, et cetera. And it's the next chapter. And now the question is this easily tricked? Is this one where a fake thing could trick you? So this paper concludes, thus, we find that in the Majorana regime, the position of the Coulomb blockade peak, even if those are thermally broadened, can be used as a sensitive probe of the ground state degeneracy splitting due to finite length of the nanowire. In this sense, our findings corroborate the conclusions of reference 44, which was the experimental paper from the previous slide. So far, so good. But all is not well. The peak amplitudes weren't exactly what they should be, and there was some mystery remaining. But at least it was like a next step forward and a next set of tests that would be harder for a faker to fake. And that was how we addressed the problem at the time. I'm going to, first of all, I'm going to see what time it is. It's 12:28. Okay, fine, good. Let me switch subjects a little bit now to some cool, interesting surprises, I would say. Well, it's not so much of a surprise because just about the same time, yes. The red shirt. Yeah. Oh, you're looking for the microphone. Yeah. I didn't mean to call you red shirt. What's your name?
Pierre-Olivier.
Red shirt.
So just before changing subject, I was wondering if it was possible to use, instead of nanowires, like 1D organic conductors or superconductors.
Yeah, well, I'll make a comment, which is that the ingredients that we needed were a few. I'll use your question to reflect on what were the key ingredients. There needed to be spin orbit coupling. There needed to be coupling to the superconductor. Probably you could get organics that had this other thing. But then there was one other ingredient which is tricky, I think, with organics relative to these semiconductors. And it's unobvious, but it's good that you bring it up because I want to mention it explicitly, which is the G factor. The reason that, who cares about G factor? The reason the G factor matters is because I needed to have a Zeeman splitting in the nanowire that exceeded the gap of the superconductor. Now, if I normally put a Zeeman splitting on a superconductor, which is comparable to the gap of that superconductor, I kill superconductivity. That's the Klogston limit. Superconductivity, rather be a singlet, superconductivity is gone. So, I need to have a system in which the material that is being proximatized, this wasn't emphasized in those early theoretical papers, but it turns out to be absolutely vital. Actually, it was, but it wasn't like front and center. Absolutely vital that the G factor has to exceed by a considerable amount the G factor 2 of the metal. So go find me an organic material, it's fine. And actually, I'm willing to give you back the spin orbit coupling Because one thing that you can do is you can, for instance, put a helical magnet on the surface and you can make spin-orbit coupling in real space instead of momentum space by just using a winding magnet. So there's ways around, like you could even use graphene if you wanted to, as long as you have a magnetic field that has spatial structure on the length scale of what was comparable to that spin-orbit length. So you can play some other games to get the topological region if you don't have spin-orbit coupling, but I don't know how to do it if you don't have the G factor. I mean, I don't know, maybe we could think about it, but that's kind of my long answer.
Thank you.
Yeah. Yeah. I would love to.
Yeah, to be honest, I don't understand like the structure of this peaks at I don't know, like this image of the right top. So because why is there no peak at 3 anymore when there are Majorana's?
You mean this stuff over here? No, here.
Upper one.
Upper
Because
here.
I would expect that like if there is a peak in the normal, like in trivial state, then also when there are Majorana's, you would still see like a peak there.
Yeah, those horizontal black lines are peaks.
I think that her question is,
Yeah.
before there's a peak at 1 and 3,
Yes?
why is then afterwards not a peak at 3 and 2, but instead at 3.5 and 2.5?
Yeah, exactly.
Oh, okay. It's important because these guys split, and this becomes the new state. So you can do it with your eye. There's an easy way to do it with your eye, which is look where that crossing is right there, and then look where those crossings are down there. You see, they're not aligned. This crossing is at some number 1, okay, fiducial number 1.
Wait, are you plotting the, because I thought it makes sense to look at the minimum of this parabola.
No, this crossing point is when two states are of equal energy. When they're of equal energy, that's when the Coulomb blockade peak occurs. Okay? And then now you see that the new equal energy points are offset by a half.
Yes. Okay, makes sense.
Good. Yep. Okay, let me switch topics. Early on in this paper and others published nearby it was an alternative route to finding topological superconductivity that did not require, and this is now again getting back to the red shirt question, did not require the application of a large in-plane magnetic field. It said instead of the large in-plane magnetic field, you can make a kind of a pseudo-Zeeman field by using an insulator that happens to be ferromagnetic. And that the scattering of the Cooper pairs off of the surface of the ferromagnetic insulator could Zeeman split them. This was known physics at the time, and I'll show you some of that known physics, but that you didn't need to apply a magnetic field. You only needed to scatter off of the surface. I think, in fact, that it was our previous speaker, Jason, who recognized, maybe subsequent to the publication of this paper or soon thereafter, you could just apply a magnetic field. Isn't that funny that it was like this crazy, complicated idea that came first and that it needed to be pointed out? A Zeeman field would probably do just as well. I don't know if that's the actual history, but that's at least my reading of the history, was that all of us chased after the application of magnetic fields because of him. But that the earlier idea was using this ferromagnetic insulator, which now I would like to go back to and play around with. Now, Jason's probably going to say, oh no, all of the ideas came from our session chair, a decade earlier or something like that. But, so keeping track of the history of this is almost impossible and can only lead to trouble. But that's at least my reading of it. But that this idea didn't get much airplay for the first 10 years after this paper. But we started playing this game. And again, it's an old problem, and I'm only wanting to show you these slides to give you a sense that even back in the 1980s, people were already doing things like putting ferromagnetic insulators, in this case it happened to be europium oxide, which is a ferromagnetic insulator, on superconducting aluminum, and seeing things like split density of states. Now remember, it's an insulator. You're putting an insulator on top of a superconductor. So you might think, well, it's not going to do anything. It's an insulator. But the scattering, even just those first few atoms, when it would scatter off of the insulator, was enough to dramatically split the density of states in the superconductor. And not only that, but the superconductor thought, based on this splitting, that it was in, depending on the external magnetic field applied, somewhere between 1 and 2 Tesla of external magnetic field, just from putting this material on top of it. So that does seem pretty enticing. And this field modernized itself, and you can now, it was studied extensively by Tedros and Meserve at MIT, and now taken over by Jagdish Mudera, also at MIT, of how, as a function of thickness of the film, the effective magnetic field would, so this is for, for 1 over, so this is 4 nanometer film, thicker, 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 but as the aluminum film became very thin, this really felt like it was in a 4 Tesla magnetic field. It's remarkable that you're putting, I mean, I don't know, I found it remarkable that you're putting an insulator on the surface of a superconductor, and just because that insulator is magnetized, the superconducting density of states in the superconductor splits as if it's sitting in 4 Tesla. I don't know, again, I personally don't find that particularly intuitive. I only want to mention that this field has continued to advance and that there's a whole literature on it, all the way through, in this case, 2017 in Physical Review Materials. And you can learn about it, and if you want these slides. So you see that the legacy of Tedros and Meserve from MIT from the 1960s, 70s, 80s is now carried forward by Jagdish Mudera. These are experiments in Francesco Giazzotto's group, where as a function of the external magnetic field, you see this splitting of the density of states. This is a tunneling experiment in which one aluminum is just a tunneling contact, and the other aluminum is sitting against europium. In this case, now they've switched from europium oxide to europium sulfide, another ferromagnetic insulator. And the splitting of the density of states is here in this aluminum. This is just a tunnel, and they're tunnel injecting from that untouched piece of aluminum. So if you like that subject, you can do it. If you like the theory of that subject, there's one other interesting thing. Let me just finish my sentence and then I'll stop. Which is, there are different kinds of scattering also inside of the aluminum in this case, or as in our case, the semiconductor, including spin-orbit coupling and spin-flip scattering, and all of how those affect the superconductor ferromagnetic insulator effective magnetization has been calculated theoretically. Not all of it has been measured because you don't have a knob on spin-orbit coupling often. But there's some interesting and counterintuitive things. Here's an example. This same term, tau Sn, could either be spin-flip or spin-orbit, depending on whether it's positive or negative. You see it's a difference between those two divided by the sum. So if I show you here for spin-flip relaxation by putting beta equals +1, so this is dominated by, well, maybe I got that backward actually. I think I might have written this backward. Yeah, that should be -1, sorry. That as you turn up the spin-flip rate, this kills the effective magnetic field, the magnetic field that drives it normal, whereas if you have spin-orbit relaxation, that should be beta equals +1, it actually gets higher. So when you add spin-orbit coupling, it tolerates a larger and larger magnetic field. If you add spin-flip scattering, it kills the critical magnetic field. So it's a subtle problem of how does spin physics, superconductivity, and ferromagnetic scattering all affect this result. And this is a really nice long review article from 2019 if you want to kind of get into the field. Yes, you had a question.
Yeah, so in the previous slide,
Yeah.
I was curious about so you can see that those peaks don't really look like you're adding the density of states up for the 2 spin channels. So for example, the outer peaks in the black curve are smaller than the inner ones.
Yep.
Right. Is it like some bias dependence or something else? Or
See, this is the hazard of talking about this stuff. Like the first time I've talked about somebody else's experiment, I'm already in trouble. I have no idea. You mean, why is the outer one different than the inner one?
Yeah, I would expect the other way around.
I don't
right?
know.
I mean,
I don't know. I don't know.
outer peaks.
I mean, in an ideal world, they would be equal height. Now, remember that this is a superconductor tunneling experiment. So there's a convolution of the density of states of one superconductor against a split density of states of the other. So it's kind of a, it's not tunneling, it's not energy spectroscopy. I'm doing this with my hands. I'm trying to look like the coherence peak of a BCS density of states moving against, and I have to do 4 fingers because this is a spin split density of states. So I have to drag a square root singularity across a spin split density of states and measure the tunneling. Okay, and what you're going to ask me is what should it look like? And I don't even have an intuition for what that should look like, but I'm not shocked that one of the peaks is different than the other.
Right, yeah.
Okay. Anyway, so it's an interesting theory problem when spin, superconductivity, ferromagnetic scattering all get involved. Now, recently, there's been some study, again, carrying on with Jagdish Mudera and Patrick Lee and others, and a host of the student, I think, Mana, was doing this, in which this very same material, europium sulfide, was put on top of gold. And in this case, the vanadium acted as a superconductor. This was the vanadium, proximatized the gold and kept the vanadium from oxidizing, and the europium sulfide sat on top. And the claim in this paper was that at the exact interface where superconductivity, ferromagnetism, proximatized through the gold in this case, met, there were these striking Majoranic peaks if you looked at the right place. And this was just an island of europium sulfide. Here's the island. And they applied an external magnetic field to magnetize it, and they saw these zero bias peaks. So it's already kind of coming into topology that you might be able to use this. It's, I think, the first experiment after this theoretical proposal. I would say a little bit of a clunky geometry, but first experiment out of the blocks was claiming to see these zero bias peaks in the vicinity of the interface between the europium sulfide and the proximatized gold underneath it. Our approach was to take the same idea that we had when we started growing the epitaxial aluminum on semiconductor and try to do the same thing again with this ferromagnetic insulators. And the shocker is it worked. And you say, how on earth could you get, okay, it's a miracle enough that you've got epitaxial growth of a non-lattice matched aluminum on top of an indium arsenide semiconductor. But to get epitaxial growth of europium sulfide on top of indium arsenide with aluminum on top of that seems borderline crazy, except here's the data. So there's the europium sulfide, there's the indium arsenide, there's the crystal interface, and here's Peter Krogstrup, now a professor at University of Copenhagen, growing these interfaces. We're not quite there yet. We have to take one more step and put the 3 materials together: semiconductor, ferromagnetic insulator, and superconductor. Here is indium arsenide, europium sulfide, and aluminum. And you can see it's not the greatest interface. It's not planar. It's crystalline, but it's not planar, and there's rough spots, and the rough spots are serious. But and the growth directions are the ratios. Look how they go. It's in a 2-to-1 ratio at the interface between the indium arsenide and the europium sulfide. So what we did was a collaboration with Cam Moeller at Stanford University, used this to measure the magnetization of these wires, and saw the important observation was that you only get magnetic fields at the ends of the wires. And this is, if you remember how magnetic material behaves, magnetic fields come out of the ends. They don't exist near the middle. Here's a simulation where you measure the magnetic field. This is for different thicknesses, but what you can see, this is a log scale on the right, but let's just look on the linear scale. The only place where there's any appreciable magnetic field, actual B field, is at the ends of the wires. Everywhere along the wire, the B field is actually 0, even though the superconductor thinks it's in 4 Tesla. There's no magnetic field there. So this is a really remarkable physical system. And so we went back to our old game of putting the nanowires, only now there are these more complicated nanowires. The great thing is that we should be able to do this without any externally applied magnetic fields. So here's what things look like. Indium arsenide nanowire, There's gold contacts so that we can measure what we're doing, and aluminum and europium sulfide. And we've picked a particular interface configuration that looks like this. Now, you might not like that one. You might wish that something was on top of something else. And, okay, we picked this one. And the aluminum had to go on last. This was a problem with the aluminum had to be cold, but the europium sulfide didn't like being cold. So we had to put them on in this configuration. Anyway, this is what we did. Now, it's interesting. Let's look as a function of the externally applied magnetic field. And here I'm using, for the first time in my life, and maybe the first time in your lives, I'm using the letter H to represent externally applied magnetic field, and it's in units of Ørsted, and he was Danish, so that's cool. So applying just a few millitesla of externally applied magnetic field, you see an interesting thing happen. As I sweep the magnetic field from negative to positive, look at what happens to the critical current. I'm sweeping up every time, and black means zero resistance. So black means it's superconducting. And I sweep up, and it goes normal. And it goes normal, it goes normal, except right here, it goes way high before it gets driven normal. And then when I sweep back the other direction, the same thing happens in flip reverse. It goes normal except right there where the critical current is 3 times higher than before. Now, what do you think is going on with that magnetization? Well, that was what our idea was. Here was the critical current, which I'll get to the theory of how we did this later, but let me just go quickly now. You can go from critical current to critical temperature, effective model of the critical temperature, and the effective model of critical temperature has these spikes in it. Well, we know from Abrikosov-Gorkov how an externally applied magnetic field will reduce the critical temperature, so we can go from the effective critical temperature to the effective Zeeman field. And from the effective Zeeman field, from the pair breaking parameter in a Zeeman magnetic field, we can find B effective for this system, and it looks like this magnetization curve. And now, everything should make sense to you. Because the reason that those spikes are there is because that's the coercive field. That's the field at which when you pass back through the magnetization, you have to go through zero. So right at that moment, the system is unmagnetized. And right at that moment, there's a great big critical current. Then you turn around, you go the other way, you go through zero again, and there's a great big critical current. Now, a new physics problem, and I will tell you for you theorists who are here to jot down new physics problems. When I say the average magnetic field is zero at this point, what do I mean average? Well, what I mean by average, because it's a ferromagnet, there are domains, and I'm just demagnetizing the domains. If the domains are small compared to the coherence length, then the superconductor just sees a bunch of averaged domains. And that's what you could say by averaging. If, on the other hand, the domains were large compared to the coherence length, that's a different limit. In that limit, superconductivity only exists at the domain walls, and it has to percolate through the system. So it's a very interesting question if you have a ferromagnet with domains and a superconductor with a coherence length. What does it mean to have this spike as the average goes through zero? Average over what? Open problem. Okay. Just to show we're not totally crazy, if we grew these in a slightly different orientation by putting them on not touching interfaces, so now the aluminum is on one side, the europium sulfide's on the other, it does a little bit, but it basically doesn't do very much at all. It doesn't, and what this means is that this is not about the europium sulfide affecting the indium arsenide. It really has to touch the aluminum. It's the interface of the europium sulfide and the aluminum, and then that spin split aluminum proximatizes the nanowire. Well, let me cut to the chase before I finish this part of my presentation. As we change, in this particular case, there's a couple of voltages. We want to change the density inside the wire, and when we change the density in the wire, we have to change this constriction voltage, but we can find an iso line in which we're changing the backgate and the constriction in which the same thing happens, but we just have to move along this wire. And when we do, to change the back gate along either the upper gate or the lower gate, what you can see is, and I want to emphasize, this is 0 magnetic field. This is after we've swept up the magnetic field, come back to 0, and there's no external magnetic field now. The wire thinks it's in a Tesla and a half, but there's no applied magnetic field. And it doesn't think it's in a Tesla and a half of magnetic field because of the magnetic field from the ferromagnetic material. There is no magnetic field from the ferromagnetic material except at the very ends where it comes out. It's just scattering off of the ferromagnet. And what you can see is it makes a 0 bias peak. Huh. Well, if you've been paying attention to the talk, you're probably now saying, I wonder what that is. And I wonder what further tests they have to do to find out what that 0 bias peak is. It's enough magnetic field, the spin-orbit coupling is there, and the Zeeman field comes from the scattering off of ferromagnet. So you will not be surprised. Oh, there's one other thing to tell you which is cool, which is when you go back through this coercive field to find the 0 of magnetic field, the 0 bias peak disappears. Just when you sweep this way, it disappears right at that coercive field. When you go this way, it's just at that coercive field. So you can shut it off, and then it un-0 bias peaks the 0 bias peak. So not surprisingly, and this is where I'll end, what happened, just about the time we published this paper was, people jumped on it. And they said, okay, here, they measured 2 things. They measured one with the aluminum here, and the other one with them there, and here's where the wave functions sit. And here are the topological regions in which this system should have topological superconductivity. Okay, I'm going quickly through these theory papers, but there's the reference if you want to find them. And then here's another one which said, the same setup with them over different people. But similar analysis, finding the regions where there's a topological phase where the wave function can sit at the interface between these 2 materials. And when they're non-overlapping, it's very hard to find topological regions, although not impossible. But the topological regions were much more prevalent when they were there. So here's another one from these students in Berlin. And here they find that, in fact, it was like in the Mudera experiment, that it was sitting at the interface between the superconductor and the ferromagnet that made the most difference. And at that interface, so what they say, we conclude that the most viable mechanism for topological superconductivity relies on a superconductor-semiconductor ferromagnetic arrangement of its constituents in which the spin splitting and superconductivity are independently induced in the semiconductor by proximity. So it needed some direct induction as well as the induction in the superconductor. And now we have a much richer understanding of where in the phase diagram this triple component system will have superconductivity. One more, where the electronic properties, this is from the Delft group and some Niels Bohr Institute people, again, studying what the wave functions looked like and where the topological regions were in this phase diagram of this hybrid material, showing that in fact the topological space was equivalent. Us, not being content to rest, went on to do other things like going back to these Coulomb blockaded objects, the inside-out version, S-I-N-I-S, N-I-S-I-N, except that the S in the middle now was the spin split superconductor in the middle. And now you can see again, even, odd, although it may be odd, even, it depends. You have to analyze this to find out. But for sure, it's keeping track of the total number of electrons. Even in the presence of the ferromagnet, you haven't destroyed parity in the system. And so the analysis ends up being rather complicated. And you have to say, with the odd case, what are all of these structures and where are the levels inside? And I think that for the sake of, finishing my talk, to let people breathe a little bit, it's a complicated system. There are spin split levels in between these normal source and drain, and the spin split levels contribute for either the even odd case with these kinds of processes from the gap or the spin split level or these others that you have to account for. So it's a rather complicated process, but you end up with numerics that look rather like the data with the same features that suggests that we understand that the Zeeman field inside of these wires is actually bigger than the gap and has pushed the system clear into this single occupied regime. I think that this is where I want to stop. And if I can just summarize, I want, if nothing else, if you are a theorist, to take away the logic of experimental physics. I think that that was the most important message that I delivered. There were a lot of details, a lot of cool data, et cetera, but the real important message that I want to convey is what does it mean to have data followed by interpretation, and that you don't get to set the error direction. You just have data and interpretation. Thanks.
Thanks for the nice overview of the field. Do you still want to pursue the Lucian orbit model?
Me, personally? Not without a few more clever ideas. I think that my personal feeling about that is that that's a useful paradigm. But if you say, do you mean with indium arsenide and aluminum and doing it just like it's straight out of the box interpretation, I would say no, for me personally. And I think that I have a greater faith in thinking of clever ideas to go to the next step instead of just crossing my fingers and hoping for the best. And the reason why is because, to be honest, it's not me doing the measurements, it's students. You know, and I'm not sure that I want to set up an army of students for bad news. And I think it's just a very hard problem, and it's a hard problem because, you know, in a way, I was going to raise my hand and object to something that Jason said in his talk, but I'll do it now, you know, now that I have the microphone, he doesn't. Which is, you know, you said it almost in a way like, this system is robust and the Majoranas are, you know, are robust against disorder as long as the disorder is sufficiently small that it doesn't take you out of the topological region. But there was no information in the statement about whether or not that was typical disorder or whether that was extremely large disorder that would do that. And I think that one of the things that I've discovered in my own research is that two things. One, just like in this last example, the topological regions are pretty sparse in this space, even under ideal conditions. All those last 4 or 5 theory papers that I showed you, those were ideal. That was in the absence of disorder. Those were perfect systems. And you saw how big the topological spaces were. Now, add disorder, and you can really give yourself a headache. So my feeling is, I really like the problem, I really like the physics, and I think that the cycle of idea, experiment, response, idea, experiment, response, idea, it's time for it to come back to idea again.
So we're at the end of the paradigm, you think?
No, I didn't say it that way. I said it much more eloquently than that, I think.